be something you can do with the way that this looks. That's kind of what I wanted to say. The way this looks. Right now it looks like 5 over x, the cosecant of x. And if you're like, Miss Naylor, I don't know how to plug in 0. Well, join the club. Okay, I'm not really expecting you to know how to plug in 0 because the cosecant of 0, I mean, you could try to think about that. Okay, but this problem is more to get you to change the way it looks. Now, it's great to be looking back at your notes. I mean, actually, it's kind of why we take them, right? That you look back at them. There's been a couple examples, not many, but a couple examples that have used trig functions. So this problem kind of fits into that category. And you might see something helpful. You're close. Not yet. It won't be that trig function. Good. You're close. I'll tell you guys, it's a good job. This is a good sign. This is a good sign. What's a good sign? Can you complete the joke? What's a good sign?
1 over cosecant.
I'm just going to repeat that. No, I'm going to repeat it. Very, very good. 1 over cosecant is the same as sine. Okay, it's really good. 1 over cosecant is the same as sine. Now, really good. I mean, I saw a lot of you write sine, or you knew it was something with sine. Really good. Maybe you just weren't sure kind of like where you write everything else. Well, take a look. I'm trying to show you that everything else just stayed put. Okay, the 5 stayed put, the x stayed put. Okay, so we're almost at the tipping point here. I mean, like, you know how to finish it?
Sine over x is equal to 1.
Sine over x is equal to 1. Now, I'm going to add one thing to that. As x approaches 0. Now, you might be like, well, what's the big deal? Well, soon we'll do another sine x over x, and x will be approaching something else. So again, as x approaches 0, you're 100% right. That equals 1. So the limit equals
5.
5. The limit equals 5. Okay, now you're starting to get it. Like, that's like an analytical method. We would say that's a little more, it's more analytical. It wasn't graphing. It wasn't honestly just straight substitution. We kind of skipped the substitution because we didn't really know how to do cosecant. But this is more recognizing that cosecant can turn into, or as was said correctly, 1 over cosecant can turn into sine. Okay, if you're like, are there other ones? Like, is there something else like sine of x over x? There actually isn't. Sine of x over x is just kind of like a special limit. So it's not like tomorrow it's going to be tangent of x over something. It's just sine x over x. It's this sort of the special one. Are you able to look in your book at page 63? Check that, 62, page 62. Page 62, number 4. If you're not able to look there, take a picture or do something that you can get involved with this. So yeah, we don't do this too much, but straight up, we're doing a problem that's actually, I'm not sure if this problem is actually in your assignment or that I assigned some other problems obviously around it. Well, we'll never do the quick review. Just let your eyes skip over that all the time. I'm looking at like the exercise number 4. But I'm just being honest, I can't remember if I assigned this one or not. But whether I assign it or not, I know this is your assignment. Okay, so you just want to kind of practice number 4. There's not supposed to be any like tricks to it. It's just kind of one more chance to practice, I guess, these 4 limits. Actually, it's 3 limits, and then letter D is something else. Again, there's not actually supposed to be like a catch to this. Sometimes students figure if the teacher's going over it, like I tend to do, that there's some reason there has to be something special about it. But it's supposed to just be a nice little limit as x approaches -2 from the left, from the right, and then letter C is kind of like the general limit. If there is any catch to this or any reason I'm going over, it's because I've seen students, when they start doing problems on their own, will often they'll overthink this asymptote. Okay, yeah, there looks like there's an asymptote right here. But I guess, honestly, the reason I'm giving this problem right now is that we can say it doesn't matter. That asymptote is at x equals 0. And that has nothing to do with x approaching -2. All you have to do is look around here. I could erase the rest of the problem, and we could get our answer just by looking right here. So don't worry about what's going on over here at x equals 0. You just want to approach -2. Okay? You should have like 3 answers. You should have 4 answers that are all the same, right? They should all end up being 3. They should all end up being 3. Okay, which is this height right here. Now, it's not only the intended height, but it actually turns out it's the actual height. And that's why this last answer is 3. This isn't working. Anything that we can clarify here? All right, you guys, you're strangely quiet. I'm used to like a lot of noise. We have a couple boys in the house, actually normally 3, but one went away. I got a dog and a cat. I mean, there's usually some kind of noise and commotion. Are you guys all right? Okay, like make some noise or commotion maybe. I want to show you one more function. It's interesting. It's a function that, I mean, somebody could have showed you in an algebra class. They usually don't, but it's not like the function itself is anything spectacular, but it's a new function for kids, and it has some interesting limits. So we're going to talk about the function, and then we'll get to the limits, and this kind of will officially then end this section. It's called the greatest integer function. The greatest integer function. Like I said, someone could have talked to you about this 5 years ago, and you would understand it. So let me talk to you about it, but then let's do some limits. The greatest integer function, just like any function, you plug into it, and then, input gives you output. The notation for it, though, the notation is different, okay? When you see like a bracket, when you see a set of bracket around x, that is referring to this thing called the greatest integer function. Also, textbooks and teachers like to abbreviate it as INT. And again, that stands for the greatest integer function. And I say, so what is the function? Well, the function is a rounding function. And it goes like this. I'm actually just going to say it. It says that if you input something, the output will be the greatest integer that's not greater than x. Let me say it again. The output will be the greatest integer that's not greater than x. So if I input 2.2 into this function, the output would be the greatest integer that's not greater than 2.2. The greatest integer that's not greater than 2.2. Now, the reason it would not be, it's all right, I'm actually glad that you said that. It would not be something like 2.19 because that's not an integer. The output has to be an integer that's not greater than 2.2. Try again. 2. Oh, okay. So 2 is the greatest integer that's not greater than 2.2. What do you think? Catching on? It would be 1. 1 is the greatest integer that's not greater than 1.9. 5. So I input 5, I output. What's the greatest integer that's not greater than 5? Okay, I see some 4s. I can't see like in everybody's head, but I see some 4s. I see a 5. Any other takers? Usually that's the question, is it 4 or 5? Is 5 an integer? Yes. Is it the greatest integer that's not greater? Is 5 not greater than 5? Sure. 5 is not greater than 5. It fits the definition. Okay, so that's what happens when you input something like that. Let's do one more. F of negative 1.8. F of negative 1.8. It would be. Did you guys just think a little bit about negative numbers? Negative 2 is not greater than negative 1.8. Okay, now sometimes kids will say, you're just kind of rounding. Yeah, we are. We're just kind of rounding to the nearest integer that's not greater than x. Okay, that's really what it does. Now, why are we talking about this? Like all of a sudden in calculus? Well, it's got some interesting limits. But to understand those limits, it's usually helpful to see the graph. Okay, I don't want to spin this that like you can't use a graph to do a limit. It's one of the primary ways to do limits. It's just that sometimes you have no calculator, no graph ways. So we're trying to kind of mix this all together. Now, just to get the graph rolling here, let me see. If you would plug in numbers between 0 and 1, so, 0.1, 0.2, 0.3, are you thinking, what's the output if I plug in 0.1, 0.2, 0.3? It would be 0. It would be 0. So my graph would be a horizontal line. Notice the filled in and open circle parts, because what happens when you get to x equals 1? What happens when you get to x equals 1? Well, the output would be 1. 1.1, 1.2, 1.3, 1.4, of course, would all output 1. And then what happens when I get to 2? Well, when you get to 2, the greatest integer would be 2, 0.1, 0.2, 0.3, all the way to 3. Okay, usually you kind of get the idea there. What we're making is called a step function. Okay, if Mario was trying to get to, I don't know, where does he try to go? No, I'm thinking like Super Mario Brothers. My middle son Caleb, he used to like dominate that kind of stuff. So I don't know. I can't remember though. He's jumping around, doesn't want to bang his head or something, but he's stepping. It's a step function. You like jump from step to step. Negatives. They would also occur. Here's what I need students to hear. It's always going to be this graph. Just like next day you graph a parabola, it's going to look the same as the parabola you graphed the day before. X squared is always going to be a parabola. Greatest integer function is always going to be a step function. Okay, so it's always this graph. All right, I promised some limits. So here's 3. They don't always come in a triplet like this, but honestly, a lot of times we're going to ask about one, we'll ask about the other. And I hope you're thinking about this, because you just need to be looking at the correct step. Are you looking at the correct step? X approaches 1 from the left, from the right, and we have like the overall limit. So Colin, what did you say for X approaching 1 from the left?
I said 0.
You're right. Okay, so X approaches 1 from the left. It would be Mario's right here. All right. Now the intended height is 0, like the whole time. How about for the right, Emma? Okay, so Mario is right here. I guess he's walking backwards. I think Mario could do that. My older son, Adam, won a TV last year. He shot like a half-court shot at that one basketball game. So that was pretty fun because, we got like a new TV. Dad doesn't buy new TVs unless they break. I think some of the kids are thinking about like just breaking the TV. So he hung up the new TV for a while until Adam went to school. I said, your TV, you can take it to school. I wasn't real fond of him taking a TV to school. But anyway, he's a young adult. So anyway, new TV on the wall. It was a little better than the one we had. The only problem was you couldn't hook up the Wii. We still have a Wii. And the reason we couldn't hook up a Wii is because it didn't have the right jacks in the back. So anyway, Adam took the TV to school. Dad hung up the old TV, and it had the jacks in the back. So the kids played a little Mario Kart. Anybody still have that, like, in the console? Yeah, it's fun to break out. You just got to have the right jacks in the back of the TV, or get an adapter, right? All right. So anyway, how about the overall limit? Overall limit. Why?
Because limit of left hand and right hand limit aren't the same.
You got it. Okay. Greatest integer function. It's always that graph. You can think about some other limits when you see that, like, in your assignment. Okay. All right. So you want to start that assignment. We kind of took an extra day on purpose. Love to see you, like, really get started with limits well. I will give you a work period Monday, but as with any work period, it's always a great idea to start the assignment before you come to class.